for our Compute 30 webinar, Build, Compute, Visualize with Jarvis. As always, we promise to keep the presentation to under 20 minutes to give you plenty of time to ask questions without going over the 30-minute limit of the webinar series. We will be answering questions at the end of the presentation, but feel free to go ahead and type them into the questions section on the GoToMeeting panel. It should be off to your right. Without further ado, I'd like to turn the presentation over to today's presenter, Nimbix's CTO, Leo Ryder. Leo?
Hi, Paul. Thanks very much, everyone, for joining. Thank you, Paul. Let's go ahead and get started. So today's webinar, again, is titled Build, Compute, Visualize with Jarvis. I'm Leo Ryder, CTO of Nimbix, and I'm very excited to be presenting to you today. So what we have on deck today, just a quick agenda. First, we're going to actually go over a very brief journey of how we actually arrived at Build, Compute, Visualize. It's a very interesting story that we want to tell. Then we'll talk about some use cases, how this process methodology applies to different disciplines and problem spaces. Then we'll get into architecture and deep dive. So we'll actually look at the Jarvis architecture on the back end, and we'll talk about how to leverage that and some example implementations and so forth. And then we'll open it up to Q&A, as Paul mentioned. Just keep your questions coming, and we'll answer them once we're done with the presentation. So the journey of Build, Compute, Visualize. How did we get here? First, everything starts with a problem to solve, and of course the solutions on the market at the time were inadequate, so the vision of the company saw this problem and decided to address it due to the inadequate solutions. The problem being that massive amounts of data, whether it's scientific or business, in just about every vertical being collected and needs to be processed. Without processing the data, it really doesn't do us any value to collect it. So what this results in is a massive, insatiable demand for computing time as a result of all this data. So what technologies and solutions existed? Obviously, you could build your own HPC cluster, but this requires, high-performance computing hardware, high-performance computing skills, which are hard to find and expensive, and of course, a data center that's capable of hosting a high-performance computing cluster or supercomputer. So all this added up to a very complex and very expensive proposition. The next option at the time, circa 2010, was infrastructure as a service, which was the dominant cloud computing platform. And, obviously a lot of promise, a lot of scale, but unfortunately the most popular implementations of this were deployed on commodity hardware, so it didn't really increase performance in any way. With the virtualization overhead and hypervisor tax, in fact, it was detrimental to performance, oversubscription, slow interconnects, and it still resulted in a very much of a do-it-yourself type scenario where even though you could provision these instances, they were basically no different than just standing up servers and installing software on them. So really, the technology was designed for web services and not actually HPC. So the founders of Nimbix decided that they would actually articulate their thesis as to what they wanted to build and what HPC on demand actually should be. So first and foremost, obviously, cloud-based. We wanted elastic scale, and we wanted self-service in a very reliable and straightforward way. Bare metal performance, very, very key to high-performance computing applications. Obviously, we work day and night to get that last little bit of performance. It would be a shame if suddenly, we had to use a hypervisor or device abstraction or all these different technologies that cause our software to actually slow down. So the company actually patented this concept of reconfigurable cloud computing, which is a bare metal orchestration type of technology. And we also have a patent pending on technology for workload isolation around this reconfigurable cloud computing. The next big thing was heterogeneity, and this means that obviously, different problems lend themselves, to work better and be solved better on different types of architectures, accelerators, interconnects, etc. So it was not about, providing this sea of generic instances or generic servers. It was about, different types of accelerators, different types of CPUs, InfiniBand, Ethernet, all these different things. But also not just the hardware and the resources, but a multi-step, multi-platform workflow. So a lot of the application and problems that are being solved actually have to go through a multi-step workflow. You don't just upload data and process it. You have to first prepare it in a pre-processing stage, then process it, then do some post-processing. So the ability to have a workflow-centric, heterogeneous type environment was very key. And of course, ease of use, maximum time to value goes without saying that if you can't actually consume something, or if it's too difficult, or if it's really no easier than just doing it yourself, there's really no sense in actually using it. So the first product of this concept was the accelerated compute cloud. And what this really means is all these different pieces that are basically brought together in a cloud computing umbrella. You had your heterogeneous hardware, so you can see different types of coprocessors and accelerators. You have distributed storage because, again, we wanted to be able to support if you have your files on third-party object store, if you want to use our file-based storage, or even customized block storage, and then a diverse application set. So things like big data, seismic, CAE, and of course bioinformatics, and a numerous amount of other types of solution types. So this is what really kind of makes up the nucleus or the makeup of the accelerated compute cloud. So the next step was really what we call putting it all together, and this is where NAC, the Nimbix Accelerated Compute Cloud, the NAC API, and what you guys know of as the NAC portal, the web portal, came together. And what this allows you to do is to take data and process and actually feed it into the Accelerated Compute Cloud and get results, either on external data or on files that you can download. So it really put process and automation around the concept of this heterogeneous, Accelerated Compute Cloud. And on one hand, you have a processing API that can be accessed through the web as well as the command line with automatic data movement in and out of third-party object store, or data in place in our own files. And on the other side, you have this web portal with a responsive UI that you can access from any device, and it works hand in hand with the API to actually submit computational workloads. Then we decided, okay, it's time to open up the platform, and this is where JARVICE was born. And what really drove this technology was the fact that Nimbix would not be able to scale to support every single application type in the world that you could possibly do with HPC. So what we wanted to do was actually open up the platform to developers as well as independent software vendors and partners and integrators to be able to take your own applications, develop them, test them, snapshot them, repeat the process, maintain them, all these different things, and either use, leverage the compute cloud as is, or, have us promote them to what we call the public application catalog so that other users could also consume these applications as if Nimbix had actually onboarded the application ourselves. So this really puts the power of the platform in the hands of developers and domain experts, not just the team at Nimbix to actually build applications. So it allows us to scale much, much faster and provide a much more diverse range of applications. And the vehicle that we use for application development, testing, and even execution, whether it's singular, singleton, or at scale, is called the Nimbix Application Environment, or NAE for short. What makes up the Nimbix application environment? It's really a full CentOS or Ubuntu Linux environment. You have root access. It's on bare metal. You have generous local transient storage. So our environments have typically in the range of at least 200 gigabytes of storage available, in some cases up to closer to a terabyte of transient storage. This is separate from your persistent storage, which is also POSIX compliant and seamless to access from inside the NAE. The NAE also provides full access to underlying hardware. That's all the CPU cores, all the RAM, all the coprocessors and accelerators, if applicable, and of course InfiniBand, if applicable to your application environment. And then finally, there's image management, so you can basically save, you can cancel, and you can clone what we call snapshot, cancel, and clone your changes in your application install so that you can call them up later either in the same type of environment or in a batch mode at scale, or even on different hardware without having to go back and rebuild everything again. So it really allows for a full sort of software development lifecycle that you can do directly on the cloud, and then deploy it in any myriad of different ways. So now everything started to kind of come into focus as to what this full capability actually was able to do. So first, we had this single platform, one platform that allowed you to do visual pre and post processing. So in addition to being able to use these environments to do some remote access in a shell, you can also do 3D workspace access to these environments, which presents a Linux desktop as if it was running on your own local machine. So there you could actually do design modeling in any type of 3D visualization type scenario. In addition to that, you could also do high-scale batch computation. So the same exact environment could be turned around and repurposed really with just an API difference to deploy at scale and compute, either in a distributed or a parallel form. And it also opened it up to clusters on demand. So even though, of course, our cloud has built-in workload management, we have this concept of being able to do a supercomputer within a supercomputer, so that you could take existing application suites that already have their own workload management or resource management and deploy them on demand on the cloud without us having to figure out a way to integrate it into our native workload management. Heterogeneous everything, hardware, software, data sources, and workflows, and also a unified fabric, so all of your all steps of the workflow and all application environments for a given account have access to all of the storage for that account and can actually connect and share information in real time with other environments running for that account. And obviously full automation with endless customization. That's thanks to our API and thanks to a lot of things we can do with that. So what we came up with now as a result of all this is this methodology of build, compute, visualize. And we think that it's capable of solving every problem in a high-performance computing context. So in a build side, you have development, you have pre-processing, and you have customization. On the compute side, of course, computation, transformation, simulation, sequencing, any type of large. And on the visualize side, post-processing and visualization, et cetera, et cetera. So some use cases for this technology and this process. This is how you would use build, compute, visualize conceptually to solve different types of problems. In a big data context, your capture and filtering is done in the build stage. Your analytics, where you actually compute the data, is actually done in the compute stage, obviously at scale. And of course, visualization, where you actually see the results of the data without having to download it offline and then visualize them. You can actually do it directly on the cloud. CAE, you have your pre-processing, you have your simulation on the compute side, and of course you have your post-processing where you can visualize the results on the visualize side. Oil and gas, custom RTM application development on the build side. You can do your seismic shot processing on the compute side, and then you can actually do your post-processing visualization when everything is said and done without actually leaving the cloud. And then any application that's custom, whether you develop it from scratch or you actually customize or install a third-party application, again, it's a build step. You can do your batch processing at scale in the compute step. And then on the visualize step, you can do the rendering and check the results in whatever format that looks like for that application without having to take the data offline first. Some important notes for this process. First of all, you can execute any step of the workflow at any time. So we don't make you first do build, then compute, then visualize. You may build once and compute 1,000,000 times and maybe never visualize. Or you may build, you may compute once, and you may do hours and hours of visualization. It's really application dependent. You can use any combination of hardware and any scale for any step of the workflow. So for example, you may not need 10 computational nodes to actually do your build or your visualize, but to actually do your batch solving, you may need all that power. So instead of paying for it all as a single thing, you can actually break up the process and actually have more cost-effective use of resources for each step of the process. It's hybrid cloud capable because it has an API for automation. So you may have part of your workflow on premises. Part of it may be on JARVICE, part of it may be on some other cloud. The point is that with the API and with the data movement, you can actually achieve the seamless unified workflow regardless of where your resources are. And we also have reserve capacity for long-running jobs. So some of your applications may require a custom portal. Instead of having to spin it up, and pay for it as if it was on demand, you may want to leave it running and just pay for it on a monthly basis. So we have that option as well. So we'll get into a bit of architecture and deep dive. First of all, this is the JARVICE architecture. This is basically a JARVICE pod or a JARVICE data center. And this can be either a public or private cloud. This particular example is our public cloud that you may be familiar with. So you have your front ends, your API, your drop, and your NAC, which is your web portal. That's the only thing that talks to the firewall directly. So you can access via HTTPS for your API as well as your portal. You can use SFTP and WebDAV to actually transfer files in and out of the cloud. And then, you can see at the bottom of the firewall, if your application can talk SSH or BNC, we can actually, proxy that back to your actual computing or build or visualize task. Cluster and workload management works together with data movement, and this makes part of what we call the management network. So we actually separate management and compute networks. So it's not possible for a tenant, whether it's your own job or it's, your neighbor's job, let's say, to actually interrupt or interfere with our cluster components. So you don't have to worry about that. Everything is isolated. The heterogeneous compute nodes actually live on a compute network which utilizes both Ethernet as well as FDR and InfiniBand. Of course, we provide different types of storage. We have image storage, which actually is what you save and snapshot and instantiate from for your actual applications, and then we have your persistent data store where you put your data, which is your POSIX compliant shared storage. And then we have database services that are internal to our process, and of course we derive asset management and billing from that. The way that you would actually, for example, submit a batch processing job from our portal is first you would choose the application and you would choose the command. So if the application is something that has already been promoted to our public catalog, you don't have to go through an NAE process. You'll actually see the actual application on the front page. You choose the application, you choose the command, which is the way to interact with it, and of course that's application specific. The second step would be to configure app-specific parameters and choose the scale that you want the application to run on. Finally, you would confirm by inspecting the actual API call and submitting the task. At that point, you can actually copy and paste that API call and submit it at some later date. We give you the convenience of being able to see exactly what's going to be done before we actually do it. To create or start a Nimbix application environment, or NAE, it's almost an identical process from at least at the beginning, where you basically choose your node hardware class, so whether you want 16 cores or 12 cores or more memory or different, 2 GPUs or not. You choose either to create or start. Then you basically configure by specifying which NAE or which template you want to instantiate from, if it's a create step, any optional parameters. And again, you confirm first you inspect the API call and then you submit to actually do it. So you can take that API call offline and do it later. After all this, you would actually check the web portal for the credentials and IP address of the NAE. You would then log into it, and when you're done, you would snapshot it, which would actually terminate the job, but first save the image back to our image store, so you can call it up later. And then when you look at, well, how do I use an NAE in batch mode, it's actually exactly the same as using a promoted public application on our portal, except that instead of going through that, you would actually select what type of hardware to run it on. You would select batch, then you would actually specify which NAE you want to use and specify the Linux command. This is very interesting. You can actually run any Linux command inside that NAE in batch mode, whether it's something that you developed or if you're calling a standard Linux command to do a different thing. Any optional parameters, and again, inspect the API call and submit it for batch processing. We have a command line version of the API as well, which is actually, it's called knack.cli. It's an open source Python program available on GitHub, so it's completely open source. It's cross-platform and fully documented, and what it does is it simplifies all of these things: API submission, job status query, job control, as well as uploading and downloading data in a very simple command line interface. So an example of how you would use knack.cli, let's say in a bash shell script, is really, you can see from here that you would create the API call, you would actually submit it. When you submit the call, you get back a string with the job name so that you can then query or act on it later. And then in this case, this basically does, now the job runs asynchronously, so in this example, what it does is it periodically checks to see if the job completed or not. That may or may not be necessary in your workflow, but you can see that you have these capabilities from the same CLI client. Going back to what we call reserved plus burst, this is a way to deploy applications on our cloud that we fully support. So you have some reserved capability, which is always on. And with reserved capacity, we bill it monthly in advance instead of on demand, and it is a lower rate, but you do make a month-long commitment to use it. And it gives you heterogeneous elasticity. So that means that you can have this reserved capacity, but at any time you can burst to the broader cloud with any type of hardware and still have unified data. So you don't have to move data back and forth. It's all the same data that you're using in your reserved capacity. It's API-driven, and you can burst and batch if you want to actually increase capacity. So some example use cases could be a custom portal where you have your own, instead of using our web portal, you have your own portal to submit jobs or to do different tasks, and then this goes off on the back end using the API and spins up jobs in batch mode. You could also use it for normal versus peak capacity. So if you have jobs that you know will normally run with 5 nodes, but periodically have to burst to 10, and you can do it this way to save money on the reserve capacity. Another example is what we call our HPC cluster on demand, which again, with a single API call, you can instantiate a cluster fully configured with a master and any number of slaves, and the slaves and the master and slaves have unique SSH trust plus InfiniBand set up between them. So it acts like a standalone cluster that you instantiate with a single API call. The master can be snapshotted, the slaves are ephemeral, and one example that we have, which you can actually instantiate today off of our portal, is a Torque out-of-the-box Torque cluster that you can use for applications that require their own workload management through PBS. You can use it, maybe it's for an academic purpose to actually learn how to or teach how to use PBS scripts and so forth. And another case that's very popular is using this for Hadoop, where you want to instantiate this elastic cluster and have use it for Hadoop. Here's an example of how we support ISVs. Basically, if you develop your own application, you want to be an ISV, you can promote it to our service catalog. We provide automated license management with self-service if you need that. You can update the NAE and it's automatically deployed once you've actually saved it. And we have a number of licensing and revenue models that you can use. We can either pay you with chargebacks if that's your preference, or we can provide automated self-service license management to both you and your customers. An example of this is an application that we have on our portal that's very popular. It's called MyGenius Reality Server. You can just go to our web portal and read all about it. But basically, Nimbix accounts for and reports to MyGenius for the past month use at the end of the month. And we support multiple hardware class SKUs with that. And of course, there's 2 engagement models for customers. You can either use it self-service completely, or you can work directly with MyGenius to integrate this application with your own workflows. So in the next episode of Compute30 Technology Series, we're going to get into scaling applications with Jarvis. We'll talk about the batch API in more detail for both scaling and automation. We'll look at the 2 different types of architectures that high-scale HPC applications will have on our cloud, parallel as well as distributed. And we'll talk about communication, and we'll show some examples of InfiniBand versus IP protocols and how you can leverage this with your application. Thank you very much. Paul, I'm going to hand it over to you for questions.
Sure. Thank you, Leo. We'll now open up the presentation for questions. Looks like 1 or 2 of you have gotten to put some in already, but if you haven't gotten to yet, there is a question section in the GoToMeeting or GoToWebinar panel. It should be off to your right. If you'd like to type in your questions there, we'll have Leo address those. If for some reason we're not able to answer all of the questions, we will do a personal follow-up with each one to make sure you get the answers to your questions. Let's go ahead and start out with the first one. This was one from a little bit earlier. You've covered part of this, Leo, but you may want to add some additional information. The question is, what storage options are available for applications on Jarvis?
Sure. So just to recap, there's three types of storage that are all available at the same time. There's the persistent image storage, which is where applications and configurations get installed into the Nimbix application environment. There's the transient storage, which is basically a giant temp folder inside the environment that you can use. It's local, it's high performance, but it gives you a much larger space. But of course, it's not persisted when you go to snapshot your NAE. And then there's long-lived persistent storage, which is outside the NAE and can be accessed both internally and externally. Internally as just a POSIX file system for convenience, and externally via WebDAV and SFTP.
Okay, thank you, Leah. Looks like we've got another one here. What developer tools are available?
Sure. So basically, of course, we support the full range of open source and GNU tool suites that come with the different Linux environments, just about any language you can think of. But as far as additional toolkits, a very popular one is CUDA that is automatically deployed in our system. So if you're developing computational GPU applications, you can use CUDA out of the box without worrying about installing it and maintaining it and making sure drivers match up and all these things. It's just part of the platform. And then we also support, if you happen to have a license for the Intel many-core, the Intel compiler for our many-core environments using Xeon Phi, you can basically install those tools, and our environments are already prepared for Xeon Phi access so that you can leverage the many-core processor in the hardware.
Okay, thank you. Next question is, do you support OpenGL?
We do, of course. In fact, we support it in two ways. There's the visual rendering, which is, if you wanted to use a 3D workspace to do either pre or post-processing, or if you wanted to use it for design or modeling, you can render that using server-side rendering with our powerful GPU nodes and actually remote display that in a very high-performance way. And we also have customers using OpenGL in a headless mode to render, things like ray tracing and so forth, or whatever it might be, to take some set of data and actually use OpenGL to render it into some, finalized product without having to visualize it first. So we support those two ways. Both use server-side processing of our GPUs in a very high-performance and straightforward way.
Thank you, Leah. I think we're almost at the top of the hour, so appreciate everyone joining us for the webinar. And if you missed part of it, I noticed a couple of y'all got to join a little bit late. Please, we'll have this recording of this posted out on our website on the Compute30 page, which is located under the Community tab at nimbix.net. You can see under the archive past sessions, and this one will be posted probably within the next 24 to 48 hours. Again, thank you for your time. Leo, thank you for your time as well, and look forward to talking to you all soon.
Thank you very much, Paul, and thanks everyone for joining.